Yeah, dear students, it's a continuation of the previous session, that is vapor pressure of Raoult's law. In this session, I would like to discuss about some mathematical interpretations of this vapor pressure of Raoult's law, as well as the most important things related to the deviation of Raoult's law, azeotropic mixtures, and maximum azeotropes, that means maximum vapor pressure, minimum boiling point, azeotropic mixtures and their classification. With some problems related to Raoult's law also I will discuss. Okay, let us start the session. See, in this one, first I want to discuss about one thing, that is vapor pressure of liquid solutions. This is liquid solutions. Mathematical interpretation it is, suppose the liquid is solvent, another liquid is solute, both are said to be volatile. Suppose if this is the volatile mixture, in this mixture I'd like to take A and B, the mixture. In this, XA and XB are the mole fractions of A and B, and A and B in the vapor state, their mole fractions I am considering XA dash and XB dash. And in this volatile liquid mixture, if you apply Raoult's law for A, partial pressure of A, then it will become PA proportional to XA. That is, became PA is equal to XA into PA naught. This PA naught is the vapor pressure of pure liquid A. Similarly, if you apply for this one same for B, then PB is equals to XB into PB naught, where PB naught will become vapor pressure of pure liquid B. Okay. In this juncture, if we have PA naught is greater than PB naught, we can understand that A is said to be more volatile than B, and boiling point of A is said to be lesser than the B. That is the meaning of volatility comparison. Now, in this discussion, according to Raoult's law, you can say total vapor pressure is equals to PA plus PB. That can be expanded as PA naught into XA plus PB naught into XB. If we take the XA naught and XB naught are the vapor pressures of the mole fractions of the vapors above the liquid, okay, then according to this Dalton's law, it can be written as PA is equals to XA dash into PT. From that, you can find what is XA, XA naught and PT relation here. And Raoult's law is applied in this one. Raoult's law, you know, PA is equals to, what is Raoult's law? In Raoult's law, we have told that PA is equals to XA into PA naught. So that one, if you substitute here, then you will get XA naught into PT is PA naught into XA. From that, I got XA. XA is equal to XA dash into PT by PA. Similarly, you can find XB value, that is XB naught into XB dash into PT by PB. Okay, but we know that sum of the vapor pressures in the liquid state is equals to 1, and that XA, XB values are substituted in this one. I got the relation, that is XA dash by PB, PA is PA plus XB dash by PB is 1 by P total. So here this I got by dividing this expression, both sides with PT. And now the point is very clear, is that a problem also can be done from these expressions. Okay, now we'll take a problem, that is 1 mole of heptane, vapor pressure 92 millimeter of Hg, is mixed with 4 moles of octane, vapor pressure is 31 millimeter of Hg, forms an ideal solution. Then find out the vapor pressure of solution that they are asking. You know, 1 mole of heptane and 4 moles of octane, total number of moles will become 5. I want to find the assume the mole fraction of heptane is XA, then it will become number of moles of heptane is 1 by total number of moles is 5. 1 by 5, this is the mole fraction of heptane. Similarly, mole fraction of octane can be obtained by number of moles of octane is 4 by total number of moles is 5. 4 by 5 is the answer. That I am assuming is XB. Now, what is the total vapor pressure of solution? That is equals to vapor pressure of heptane plus octane, assuming PA plus PB. Whereas if you apply the Raoult's law, PA naught into XA plus PB naught into XA. PA naught for heptane given in the problem is 92 into 1 by 5, and PB naught value for octane given as 31 into 4 by 5 we have taken the total simplification. We got 43.2 millimeter of Hg. This is the total vapor pressure of the solution. Okay, understand? Next, let us see another problem what we have solved here is at 88 degrees Celsius, benzene has a vapor pressure of 900 torr and the toluene has a vapor pressure of 360 torr. What is the mole fraction of benzene in the mixture with toluene that will boil at 88 degrees Celsius at 1 atmosphere pressure? Benzene and toluene forms ideal solution also given. So they are telling it is boils at 88 degrees Celsius and 1 atmosphere pressure means this solution boils at that means total vapor pressure will become 760. This indirectly given the information, and that is again applied for the PA naught into XA plus PB naught into XB, and here in this case benzene vapor pressure taken 900 into mole fraction of benzene plus 360 into 1 minus mole fraction of benzene I have taken. Why? Because toluene mole fraction is not required in the discussion because our aim is to find the mole fraction of benzene. So I have taken the toluene's mole fraction as 1 minus mole fraction of benzene in this one. After simplification, 760 has become 900 mole fraction of benzene plus 360 minus 360 mole fraction of benzene, and upon simplification got 540 into mole fraction of benzene is 400, and finally mole fraction of benzene upon calculation got 0.74 is the answer. So in this way you can find the mole fraction of benzene when the benzene is mixed with the toluene and boils at 88 degrees Celsius at 1 atmosphere pressure. Then consideration is 760. If this consideration is not taken, this is not taken 760, then it will be a total confusion. So this is the answer for this problem. Next question. Let us see the next question. The problem: cyclohexane and ethanol at a particular temperature have vapor pressure of 280 millimeters and 168 millimeter Hg respectively. Then if these solutions have mole fraction value of cyclohexane equal to 0.32 or mixer, and the mixer has the total vapor pressure of 376 millimeters, will the mixer be an ideal solution? See here, if they have taken that 280 is the vapor pressure of cyclohexane with the mole fraction 0.32 plus the vapor pressure for that ethanol is 168 into its mole fraction is 0.68. Approximately we got 203 value, so 204 we got. So that is the total vapor pressure from the experiment. But a mixer has a total vapor pressure given in the problem is 373. So mixer vapor pressure and the problem which is given 376. Which is greater than this value we got, so it indicates that is a non-ideal solution, and also it follows positive deviation from Raoult's law. Next one. What is the next problem I am going to discuss is this one: liquids A and B forms ideal solution, and the vapor pressure of A and B at 100 degrees Celsius at 300 and 100 respectively. So A vapor pressure is 300, B vapor pressure is 100. Suppose that the vapor pressure above the solution is composed of 1 mole of A and 1 mole of B collected and condensed. This condensate is then heated at 100 degrees Celsius and vapors are again condensed to form again liquid L. Liquid L. And what is the mole fraction of A in the vapors of liquid L? So it is a 2 times they made the condensation. So first we will consider the total vapor pressure formula from Raoult's law, that is XA into PA0 plus XB into PB0. But they are given A is the A value is 300 mole vapor pressure in pure state into mole fraction of A is XA, and B value vapor pressure is 100 into XB have taken. But they are telling one more thing, that number of moles of A, number of moles of B is 1 in the composition. So Na and Nb both are same, means mole fraction will become 1/2. So using that one, we have calculated the total pressure is 200 we got in this first case. And after that, the condensation is giving the vapors condensed and again boiled. Then vapor phase of A and B, mole fractions taken as YA dash and YB dash, applied the Dalton's law. In the Dalton's law, what we done is PA dash, whatever PA dash is there, that is 150 by total pressure is PT. Okay, that we got is 150 by 200 is 0.75, means vapor, the mole fraction of B in this vapor phase is 0.25, and that he has taken and multiplied, you got 250 in that condensation. So 250 millimeters you got, and that 250 is the total vapor pressure in the second condensate. Then after what we find is the PT XA double dash value 300 into 0.75 is 225, 250 I got 0.9 we got. So what is the value of this vapor phase mole fraction of A is 225 by 3 250, 0.9 we got. So 0.9 is the answer for this one. So here there is a continuous process. There is a continuous process of the finding the vapor mole fraction of A in the vapor phase in the first condensate. In the second condensate, what we did is the mole fractions value we got reverse to that of mole fractions values we have taken to find the total vapor pressure of that one is 250, and after that we have used the second condensate mole fraction of A vapor phase is 225 by 250, 0.9 we got. So this is one problem. So in this problem there are three stages are there. The three stages were done. First stage we calculated according to Raoult's law. The second stage we applied the Dalton's law. Third stage, the third step, that means in the second condensate case also we applied Raoult's law followed by Dalton's law. Two times we have done the calculation to find the mole fraction of A in the vapor phase of the liquid L. So these are the problems. Now I am going to discuss about azeotropes. Azeotropes. Actually, azeotropes are nothing but these are also mixers. We can say azeotropes or azeotropic mixer. The concept is azeotropic mixer. Okay. Actually, some liquids are there mixing azeotropes. They form azeotropes. What is actually the term meaning of azeotrope? It's nothing but when we have to consider from the informations regarding the non-ideal solutions here. Non-ideal solutions showing large positive or negative deviations from Raoult's law cannot be purified and distilled. Whenever this type of initial composition of solution is taken, then it's difficult. So heating changes its composition until at a constant temperature, where the composition of mixture of liquids and vapor states is constant and at the same time. So distillation does not change its composition further. So a solution at certain composition. So what is azeotrope? I am coming to the point. That is a solution at certain composition which continues to boil at constant temperature. At constant temperature without change in the composition, constant temperature without change in the composition of the solution, composition of the solution in liquid and its vapor state, and its vapor state is called azeotrope or azeotropic mixture. In a simply you can say constant boiling mixture. This is called as constant boiling mixture. Okay, these are called constant boiling mixtures. So what is the meaning of azeotropic mixture? Is a solution of certain composition which continues to boil at constant temperature without change in the composition of the solution in liquid on its vapor state. That is called as azeotrope. Actually, this type of azeotropic azeotropes are there, which are also said to be binary mixtures. Same composition liquid and vapor phase and boil at constant temperature. It is not possible to separate the components by fractional distillation. What is the importance of this one is, it's not possible to separate the components. It is not possible to separate the components by fractional distillation. By fractional distillation. So hope you understand what is azeotrope. Azeotropes are constant boiling liquids, because on mixing liquids, on mixing they generally forms azeotropes. The binary mix same composition liquid and vapor phase and boil at constant temperature. So what is the importance of this one is they cannot be easily separated by this one. Now let us see how many types are there. How many types are there? Azeotropes are of two types. Types of azeotropes. Types of azeotropes. In that, one type is called as azeotropes with maximum vapor pressure and minimum boiling point. Okay, you can understand one thing, that minimum boiling azeotropic mixtures. Minimum boiling azeotropes. Azeotropes means they have maximum vapor phase, vapor pressure. They have maximum vapor pressure and they have minimum boiling point. So usually any of the mixture is there with a minimum boiling point, definitely that will exhibit highest vapor pressures. Suppose when a liquid in a solution don't have great chemical affinity for each other. Assume when liquid in a solution do not have great chemical affinity for each other. Generally, what will happen is, the two components are there. They don't have any great chemical affinity for each other. Okay. That means they don't have any kind of this one. Then what will happen is when the boiling point is more, evaporation is more, they'll show positive deviation. So they will show positive deviation from ideality. Okay. So they're higher, definitely they have a higher escaping tendency, increase the evaporation and much more expected than Raoult's law. Okay. In many cases, what will happen, these deviations are so extreme and led to a maximum in the curve. So in the Raoult's law, the curve also we will get like this. Instead of a straight line, you will get this type of curve in the graphical representation. So now in this type, what will happen, the point of maximum evaporation means the boiling point at this composition will be minimum and constant. So at that point of maximum, the point of maximum vapor pressure means that the boiling point at this composition this composition will be minimum and constant. Minimum and constant. Suppose the minimum boiling azeotropes you want to tell components A and components B. Direct examples we have. If you take component A is water and ethyl alcohol is component B, the mass percentage of B okay is taken percentage 95.57. That time A boiling point noticed as 373 Kelvin. B boiling point is 351.3. And the boiling point in kelvins, I am writing this is boiling point in Kelvin. Azeotrope boiling point. Azeotrope boiling point is 351.1. So it is lesser than the individual boiling points. Similarly, you take water and propyl alcohol. In that, the propyl alcohol mass percentage is noticed as 71.69 and water, as you know, is 373 Kelvin. Propyl alcohol is 370 Kelvin boiling point, 370 Kelvin. But azeotrope boiling point is only 350.72 Kelvin. So these are actually minimum boiling azeotropes we can see. Like that, one more thing we have, that is chloroform is mixed with ethyl alcohol, ETOH or C2H4OH, whereas the ethyl alcohol composition is 67.00 only mass percentage. And by that, chloroform is 334 is the boiling point, and that of ethyl alcohol 351.3 Kelvin. But azeotrope is coming 332 only. So it is lesser than the boiling points of the components in the individual stage. So here what we notice is the three important things. Boiling point of the azeotrope is lesser than the constant boiling point is lesser than the boiling points of individual components. Let us see the another second type of azeotrope. Azeotropes azeotropes, we can say they are first we told that is minimum boiling azeotropes. Azeotropes are there. They are with minimum vapor pressure. They are with minimum vapor pressure and maximum boiling point. So minimum boiling azeotropes we told the first one, and this can also be called as maximum boiling azeotropes. Maximum boiling azeotropes. The second type of azeotropes is maximum boiling azeotropes. Okay. Now here what happens when the liquids in the solution form chemical bonds. Earlier there is no chemical affinity we observed. Is like they don't have great chemical affinity. This case they have chemical bonds. That means when liquids in solution form chemical bonds, they form chemical bonds. What happens? Negative deviation. Chemical bond means like hydrogen bonding concept we discussed. When the hydrogen bond is existed, when what happens? That forces of attraction between the two components is greater than the individual components. Then at that time what will happen? Vapor pressure will be reduced. So you will get negative deviation from ideality. Negative deviation from ideality. And then what happens? Escaping tendency will decreases. So escaping tendency decreases, vapor pressure also decreases. Vapor pressure decreases means boiling point increases. That's the meaning of it. Now that means the point in this one, the point of minimum vapor pressure, the point of minimum vapor pressure and the curve the graphical representation I am telling means the boiling point of this composition will be maximum. Boiling point will be maximum and also constant also. If it is not constant, it is not said to be azeotrope. We have some examples are there. If you take the components E and B and like earlier we discussed the mass percentage of B and boiling points of A and boiling point of B and azeotrope analysis, experimental analysis, then it can be given, it is given experimentally, like if you take water is A and HCl is B, chemical bond is forming, and 20.3 only the mass percentage of HCl in that. Boiling point of water is 373 Kelvin, HCl is 188 Kelvin. But here it is 383 Kelvin is the maximum boiling point of the mixture. That's why I call this is maximum boiling azeotrope. Another one, if you take water with nitric acid, you take water with nitric acid HNO3. In that nitric acid we have 58.0 is the mass percentage is there, and as usual 373 Kelvin is the boiling point of water. Nitric acid is 359 Kelvin is there, but in this case 393.5 Kelvin's azeotrope boiling point is maximum. Another one, we have water with perchloric acid is there HClO4. In that case we have 71.6 is the mass percentage of perchloric acid. while that of boiling point of this one perchloric acid is 383 Kelvin. And notice that the 476 is very strong bonds forming here. That is azeotropes boiling point is 476 km. So in that way, notice that these are the maximum boiling azeotropes. These are called maximum boiling azeotropes. So understand what is maximum boiling azeotropes? Mixture of two liquids whose boiling points are more than either of the two pure components. Here pure components boiling points, if you observe in this table column, 373 for water and 188 for HCl, but it is maximum 383 is maximum individual, like that. In the case of nitric acid and water, the same thing is noticed. Nitric acid in some books and all they are given 68, and here in this we have given 58. So 58 to 68, yes, 68 you can take. As per this explanation, the 373 for water and 359 for nitric acid, we got 393.5 Kelvin azeotrope maximum, that is greater than the individual. That of water is 71.6 in the case of perchloric acid mixture, and it is also 476 greatly differentiated. So what we have noticed here is positive deviation. What is the meaning of positive deviation? Means curve will come like this. Negative deviation means curve will come downwards in the graphical representation. Ideality is different and this curve is different. Okay. Now we'll check with another interpretation. Hope you understand this azeotropic mixtures. Now we will see one illustration in this one. Now this is the illustration on Raoult's law. Let us see the composition of vapor over a binary ideal solution. You know, composition of vapor over a binary ideal solution is determined by the composition of the liquid. That's what we observed in the previous problems. So using Raoult's law, using Dalton's law, we can do it. Composition of the liquid can be obtained from the Raoult's law. Composition of vapor phase obtained from Dalton's law. So they are saying if XA and YA are the mole fraction of A in liquid and vapor respectively, then they are asking us to find the value of XA. The value of XA for which YA XA, YA minus XA has a minimum. Okay. What is the value of pressure at this composition? Also they are asking. What is the value of the pressure at this composition? Okay, we'll check it. Now in this question, they are given very clearly, if XA and XA and YA are the mole fractions of A in liquid phase, that is XA, in vapor phase, that is YA. Then find the value of XA for which XA minus YA minus XA has minimum. Okay. Minimum value, YA minus XA has minimum value. So let us see. We know what is the mole fraction of A in the vapor phase. That is from the Dalton's law is nothing but partial pressure, that is partial pressure of A divided by total pressure. We know that is equals to, from Raoult's law, it is XA into PA naught divided by PT can be written as PB naught plus PA naught minus PB naught into XA. So we are writing everything with respect to A only in this mole fraction cases. Then you can do one thing, that is subtracting the expression both sides XA, then YA minus XA will become equals to XA PA naught minus what will come here, PA naught divided by PB naught plus PA naught minus PB naught into XA minus XA. Okay. So now differentiating with respect to XA, what we will get here is, if we differentiate with respect to XA both sides, what we will get is d by dXA of YA minus XA will be equals to equals to PA naught divided by PA naught divided by the entire expression, that is PA naught minus PB naught into XA, that value NCM is there, PB naught will come minus what will come, that is XA into PA naught into PA naught minus PB naught divided by PB naught. Again that expression is PA naught minus PB naught into XA, but this time this differentiation power 2 will come here, this in this differentiation UV formula if you apply, minus 1 with respect to XA, again one more time if you do, minus 1 will come. This is the entire expression. This is the entire expression. Now the value of XA at which YA minus XA is minimum value can be obtained by putting the derivative equal to 0. So this YA minus XA will become equals to minimum when we put this value equal to 0. So then what we will get here is, in this case, we will get finally, if you solve, XA value will become equals to square root of PA naught into PB naught minus PB naught divided by PA naught minus PB naught. Hence, what will happen? The total pressure of the composition, that will become equals to square root of PA naught into PB naught. And so what is P? That is this value you will get. So this you will get when we equate it to 0. Then after you have to find the XA value. So XA value you will get, this is the value, and that XA value is nothing but the first question, that is what is the value of pressure at this composition. That is value of pressure at this composition is square root of PA naught into PB you will get. PB naught is the answer for this one. So it won't come in a minute. So you have to solve it, then you will get this value. So I hope you will cross check it, the simplification, and you will get this value. Okay. And coming to the things what we discussed, we started with azeotropes. Defined azeotropes. Azeotrope is a solution certain composition contains boils at a constant temperature, and definition given. Then after types of azeotropes we discussed the minimum boiling azeotropes as well as maximum boiling azeotropes with examples in the composition, experimental determination values. Then after this is one illustration also we have considered in this one. Okay. Now what we have noticed from these two things is nothing but azeotropic mixtures are important for the examination point of view. Okay. Now we will take another simple question now, that is which pair will show positive and negative deviation and negative deviation from Raoult's law. So what they are giving is, the first one they are giving a methanol and chloroform. Methanol chloroform, and second one they are giving methanol and cyclopentane. Methanol and cyclopentane. Here, understanding one thing from this one is very clear that in these exercises, the first one, if you observe, methanol and chloroform. Methanol and chloroform. And as we know that between methanol and chloroform, this is methanol only, first one, methanol only. In methanol, hydrogen bonding is there. In chloroform, hydrogen bonding is there. So methanol, if you take, how we can write, this is H, I'll show you, hydrogen, and a chloroform, H, CHCl3, alcohol, hydrogen is positive. So because of hydrogen bonding, what will happen? Vapor pressure decreases. Vapor pressure decreases, escaping tendency of the molecule decreases. When the escaping tendency is decreases, means the boiling point increases. Boiling point increases. And whenever the vapor pressure is decreasing and boiling point is increasing, maximum boiling compounds these are. So here boiling point increases, vapor pressure decreases, means what we have discussed in the previous point here, this vapor pressure is decreasing, boiling point increasing for negative deviation from ideality. So it is the negative deviation from ideality. So it shows negative deviation from ideality, Raoult's law. This is the answer for the first one. Now the second one, we have methanol is there, cyclohexane is there. As we know that between methanol molecules, intermolecular hydrogen bonds are strongly arranged. And in this case, if you take this example, in this one, we can tell hydrogen is positive, oxygen is negative, partially negative. And in between that, if you take the cyclopentane, the cyclopentane is going to break the bonds, hydrogen bonds between the molecules. So when the hydrogen bonds are separated out, what will happen? The escaping tendency of methanol will be increased. That time vapor pressure, in this case what will happen? Vapor pressure increases. That means volatility increases for the alcohol. Vapor pressure increases. Boiling point for the solution is decreases. Automatically it shows positive deviation. Positive deviation from Raoult's law, nothing but ideality will be noticed. So this is the answer for this question. So we can understand the interesting questions in this particular case of Raoult's law when we understand the chemical connectivity between the molecules. I hope you have understand this session. In this session, what I have made, I made different kinds of interpretations. In this, I know that there are some problems I have discussed earlier, and the problems are in related with the previous class also, vapor pressure. And the first I have discussed about some of the problems related to Raoult's law. Then after I have discussed about the most important definition for the examination point, that is azeotropes. After that, discussed some interpretations, but never get bothered about this informations and this problem. And this problem you have to solve it, then you will get this vapor pressure. And after that, I've again taken one more important problem, that is a question, that is a knowledge based question from this concept. Hope you understand this concept. And in the coming session, definitely I will discuss most interesting Raoult's law concepts of relative lowering of vapor pressure, how they are said to be the colligative properties. Okay. Until have a nice day. Bye bye. Thank you very much.